Actually, it gets very difficult after
Okay,
calculating
fine,
this thing.
fine, fine. So maybe we'll look at a slightly different approach today to the same thing, and then we'll see how to proceed. Okay.
Okay, sir.
I didn't get a chance to go over that, so I'm chasing some deadlines this week. Maybe I'll try that over the coming weekends and get back to you if that works or what modifications one need to do. We will see. Huh?
Okay, sir.
Okay. Yeah.
Sir, I have one question, sir.
Hmm.
Sir, from the starting of this stochastic process, sir,
Hmm.
we have defined, sir, Sn, Xn,
Hmm.
and
Hmm.
all, sir, Nt,
Hmm.
all these things, no, sir.
Right.
And we are saying that they are the random variables.
Hmm.
So, sir, how can we prove this one that it is a random variable? Like we
Which
initially
one is a
we
random variable?
like suppose, sir, we have to prove that the Sn is a random variable.
Uh,
So, sir, first of all, I did not recognize that what is its sample space, and from
which can you be more specific? Then I can answer this question because it depends on what the problem is, right? What the
yes, sir. So like in random variables, so when we define random variable, we need a sample space first.
correct.
So, sir, in this Asian, what would be our sample space, sir?
So, for example, if you look at the counting process, right, n of t, right?
Yes, sir.
What do
Hmm.
you think is the sample space there?
Is it infinite set, sir?
It is just a set of
But
natural
to
numbers
be very
only, sir.
specific, yeah, set of natural numbers, right?
Yes, sir. Yes, sir.
For each t, you are basically counting the number of arrivals. It could be zero, it could be one, two, three, till infinity, right? Natural numbers.
Yes, sir. Yes,
That
sir.
is your sample space. I think I answered your question, right? One part.
Yes, sir.
What else you have?
In Asian, sir, Asian is nothing but the time at which nth person arrived. No, sir.
So the time at which the nth person will arrive. Yes.
Yes, sir. So,
Hmm. So what will be the possibility? Nth person, where can he arrive?
oh, there is.
After
Zero
n minus
excluded.
1.
See,
It
zero
is.
I cannot include because you know I cannot say n people will arrive at zero, right? That is excluded from our discussion because we are
Yeah.
assuming that the arrivals cannot happen, right? So anything above zero till infinity is a possibility, right? That is your
Yes.
sample space, right? Then you have to construct the sigma algebra corresponding to that. So there also it's very easy. I'll construct the Borel sigma algebra, the usual stuff, right? Then I
Okay.
have to put a measure on that, right? So
Yeah.
what is the measure? What
So
is the
measure
measure
that
of
we are taking the probability measure only, no, sir.
probability measure? What will be the measure?
Length of interval.
No, no, not really, right? Okay, so this is lectures 18. Okay. So, in the case of, okay, let me start with that itself. So, Sn is what? Time at which nth arrival happens, right?
Yes.
Right. So, what is the sample space? Sample space is from 0 to infinity, right? Do you agree?
Yes, sir.
Sir, it should be Sn minus 1 to infinity, right?
No, Sn can be anywhere, right? So, nth arrival can happen at
No, it
nanoseconds.
can up. No, sir, it can.
Sn,
No,
what will be Sn? Tell me.
time at which nth
So,
arrival
what
occurs.
can that time be?
It
One
should be
second,
greater
2
than n
seconds.
minus 1 arrival.
No, what is Sn? I think you should understand that properly first. Sn is the time at which nth arrival happens, right?
Sir,
Uh, at what time nth person can arrive?
Sir, here random is the time, no, sir?
Yes, randomness is in
Means
the time.
time. Okay, sir.
Yeah, so it can happen at any time closer to zero, right? That
Yes,
means
sir.
I'm saying before Sn, n minus 1 people have already arrived. Okay, that can
Yes,
happen,
sir.
right? Any arbitrary close to zero, if I take a small interval, there can be n arrivals there. There it has a non-zero problem. So what is the sample space I can do? Borel. Do you agree?
Yes, sir.
I mean, those who don't know this, don't worry. Okay, Borel. So what will be the probability measure? So how do you find what is the probability measure here? So give me any interval, I should be able to tell you what is the measure, right? Right?
Yes, sir.
Or in other words, in this case, equivalently, I can give you the density, right? If I give you density, I know the probability itself, right? So this will
Yes.
be the density. This is something that we derived in the last, but one, I think 2 classes before, right? This is the density called the Erlang distribution. Okay, there is a name for this. Okay, this is called the Erlang distribution. I think I forgot to say this. This is just a name, right? So, see, typically, I think this is an aside. So, for those who know a little bit of measure theory, so I should just say, given any interval, right? What is the probability of Sn falling in that interval, right? Do you agree, Sumit?
Yes, sir. Yeah.
Yeah. So, what is the probability that Sn falls in, let's say, some a and a plus delta? That is given by integral a to a plus
A to
delta
A plus delta. Yes.
Fsn of t dt, right?
Yes.
This
Yes,
is the
sir.
measure, right? You integrate and tell me what the answer is, that will be the measure. So I'll start with that measure. Okay, clear?
Yes, sir.
Yeah. Hopefully this is clear, right? So we will look at the proof of the Poisson. We will continue with that. Last time, I think, I'm sorry, we took a, I thought we can use that to derive, but I was stuck, right? We were stuck. Okay, so I didn't get a chance to look at that in detail and get back. So I'll do that. Ayush, you had any questions?
Hello. Yes, sir. I have a question.
Yes.
So, like, SN is the definition of SN is the number of people arriving,
No,
the
no, no,
nth,
no.
the nth person arriving at SN, right?
Yeah. So the time instant at which the nth person will
Uh,
arrive. Yes.
so, sir, see, if it is S1, then first person have arrived. If it is
Correct.
S2, then second person has arrived. So,
Correct.
and X1 is and X1, X2, X3 are the inter arrival times.
Correct.
So, sir, if we take X2, then it is S3 minus S2.
Yes.
So in that time, only one person has arrived.
Correct.
So, sir, in any inter-arrival time, only one person is arriving.
Yes. Yes. So this is x1. So if you can see, this is x2, but this time instant is s2. For example, this is s3, but this time interval is x3, and so on. This is the picture. Okay.
So, sir, like then in definition of Poisson, we are saying that it is following some exponential distribution. But in
No, no,
every
no. Huh. Go ahead.
but
Go
in,
ahead.
but in every inter-arrival time, only one person is arriving. So how is it?
No, so no. What is so this, right? Inter-arrival times x1, x2, etc. These are IID exponential. Do you agree?
Sir, okay.
Do you agree?
Sir, by definition, okay, sir.
Yeah. So now, how do we construct a Poisson process? So you take inter-arrivals as IID exponential with certain rate lambda. Okay. And then you assume that the way I'm going to generate this process has independent increments, right? Do you agree?
Yes, sir.
So if I use this and generate the arrival, the resulting arrival will be a Poisson arrival. Okay, it's called Poisson arrival. Do you agree?
Sir, but how only one person is arriving if it is following exponential distribution? That is my question.
No, no, no. So it's like this. Okay. For example, at this time, some person has arrived, right? X1. X1th time instant, some person has arrived. Do you agree?
Yes, sir. One person arrived.
This is the first person arrival. Okay.
Yes, sir. Yes, sir.
Now, what happens is, think of it as like a clock. Okay. So the clock will tick whenever, so you generate x2, which is exponential. Okay.
Okay. Yes, sir.
Okay, so it can take any value, right? 0.38, 5, whatever, 10, whatever, depending on what lambda is, and when you sample, you get any value, right?
Okay. Yes, sir.
Okay, so now let's say x2 is 3.1. Okay, so
Yes.
what I will do, I will add 3.1 to S1. That will give me S2, right? I
Yes,
will
sir.
let one person come here. The first person is coming here. The second person will come here. Okay. Again, independently generate a random variable according to exponential. That turned out to be 1.01, let's say. Okay. I'll take 1.01, add to S2. I'll get S3, which is the third person arrival.
So, sir, the time is following exponential distribution.
The inter-arrival times follow exponential because
Okay. Okay. Time.
x3 is exponential, right?
I got it.
Right?
Yes, sir.
Think of it as a Poisson clock, okay? So, or the exponential clock. It ticks after the exponential whatever distribution that's given, right? It will tick. The moment it ticks, there is a person.
Okay.
Okay. So
Yes.
the time difference between two ticks is exponential. Okay,
Yes, sir.
and if you assume that the increments are independent and stationary, that means the distribution doesn't change, then the process n of t, the number of people arrived in time t, is said to be a Poisson process. In fact, a stationary Poisson process. Okay, is that fine?
Yeah. Yeah. Yes.
Yeah. So yeah, so this is the first process, random process that we have looked at, right? In fact, we looked at a Bernoulli process, but maybe we'll revisit if possible today. Okay, so now we have to prove that the density, or sorry, the distribution or the PMF of n of t is Poisson, right? That's what we have to prove. See, when we construct Poisson process, we didn't say that the number of arrivals is Poisson distributed, right? We just said the inter arrivals is exponential and it has stationary and independent increments. Then the resulting process n of t is follows a Poisson distribution. That is something that we need to prove, right? So let's take a simpler approach. I think last time we took a slightly complicated approach and we didn't succeed. So let's look at this. Okay, so proof. Okay, now let's look at n of t. This is the process, right? Is this fine? So n of t is the number of arrivals in time t. So assume, let's say greater than, this is an event. Do you agree? So it
Yes,
is
sir.
the number of arrivals being greater than or equal to n in t time interval. Okay. So equivalently, that I can say, what is equivalent to this? Right, so I'll draw some
Sn
pictures.
less than equal to
Yeah, so I'll draw some pictures. So 0, this is t. Okay, I'm saying n of t has greater than or equal to n arrivals. That means what? That means the nth arrival should be somewhere here, right? Okay, since n of t is greater than or equal to n, there could be n plus nth arrival somewhere less than t, n plus 2th arrival can be less than t, and so on, right? N plus second 2, right? N plus 3, and so on. So all that I can say is nth arrival should be less than or equal to t, right? So that is equivalently, I can write Sn is less than or equal to t. Both the events are equal. Is this fine? Any issues?
no, sir.
Okay, yeah. So that means the probability of this should also be same. Do you agree? If the events are same, then the measure should also be same. I'm looking at the
Yes.
same process, right? Okay, okay. So now, what is this? What is probability of n of t greater than or equal to n? See, n of t is a counting, right? It's a discrete random variable. So this is same as I should start from n, go all the way till infinity of this, of the PMF, right? Okay. That I am saying Sn is less than or equal to t. That means 0 to t, right? The density of Sn of S ds. Do you agree with this? Okay. Is this okay or
Sir,
no? Huh.
Sir, NT random variable, this is a discrete and this SN is a continuous.
So yes, correct.
Yeah, for that reason we have used here the PMF and here PDF. No, sir?
Exactly. Yeah. True.
Okay, sir.
Okay. So is this clear, everyone? Okay. Fine, right?
Yes. Yes, sir.
Okay. Now let's look at this. So what is this? This implies summation I equal to 1 to n. What is Pn of t of I? Okay. What is Pn of t of I? Well, we need to show something, right? Do you agree? We need to show something here, right? So we need to show that this. Okay, let me write it like this. Need to show that this is equal to what? I need to prove that this is equal to lambda t power I, right? E power lambda minus lambda t over I factorial, right? That means I need to show that this is a Poisson distributed random variable, right? N of t. That means the PMF follows Poisson. That is what I need to show, right? Or in other words, I need to verify. Okay, so let me write that. Need to verify if lambda t power I, summation over all this, lambda t power I over this thing, this is equal to the left hand side. What is the left hand side? 0 to t, okay, fsn of s ds. Is this fine? We need to verify this. Okay. Okay, I'm sorry, this is n to infinity. Okay, clear or no?
Yes, sir.
This is something that we need to verify, right? If we verify that this is true, if this is true, then the previous expression is also true. That means Pn of t should follow Poisson, right? Do you agree? Yes?
Yes, sir.
That's easy to see because if I take the derivative on both sides, right, what do I get? So what do I get?
So RHS will be only FSN of S.
Huh? Yeah, so this will be Fsn of t,
And
right?
yes.
What will be the right hand side? The derivative of this?
Yeah, will derivative.
Huh?
So you need to calculate, sir,
What do we get?
with respect to T.
Okay, so now let me just write this in a slightly different fashion. I can write this as I equal to 0 to infinity, which is 1, minus, okay, I equal to 0 to n minus 1, lambda t power I, e power minus lambda t over I factorial, right? This is what I have. Do you agree? Right? So you are taking derivative with respect to t. What do you get? So, we have t power I and e power minus lambda t. What is the derivative of that? Okay, so let's directly do this. So t power I, e power minus lambda t. So what is the derivative? I t power I minus 1, e power minus lambda t minus lambda t power I, e power minus lambda t. Right? This is what we get. Do you agree? Okay.
Sir, you just taken the complement of that event, sir. After
Yes,
this,
here yes, but either way it is true, right? So you can either differentiate this or you differentiate this itself here,
okay,
right?
sir.
You agree? Huh?
Yes, sir.
Okay, so now if you compute this, okay, so I'll leave this as a homework. This is algebra, okay? So algebra homework. So if you compute this, Fsn of t turns out to be lambda power n, t power n minus 1, e power minus lambda t by n minus 1. What is this? Erlang, right? That is the distribution of Sn, which is true. Or you can do the reverse engineering, right? So, for example, if I can show that both the sides are equal, that means, you take nothing but Fsn of S, right? So, the summation derivative is Fsn of S. Then what should be this summation, the derivative, so that this would be equal to the right hand side. Okay, is this fine?
Yes, sir.
So one way to see this is what is lambda power n t power n minus 1 over n minus 1 factorial. What is this e power minus lambda t? So you can do the Taylor series, right? Minus lambda t plus lambda square t square by 2 factorial minus and so on, right? So when you multiply this, you let t power n minus what is this 1, right? T power n minus 1. Oh my god, what happened? Oh god. I hope it is still there. Yeah, so you just do the Taylor series and you can see that both are equivalent. Okay, I leave it as a homework. So you are supposed to show that this is true. Is that fine? If you don't get it, we will look at this again. You should be able to get this. Yes or no?
Yes, sir.
Everyone?
Yes, sir.
Okay.
Yes, sir.
Okay. So this is you can describe Poisson process in many ways. Okay, let's look at an alternate definition of what is the current definition of a Poisson process. So we said n of t is said to be a Poisson process if it is a renewal process plus exponential arrival time, right? This is how we define. Do you agree? Yes or no?
Yes, sir. IID also, no, sir?
Yeah. So independent, that renewal will tell you that. Right?
Oh,
So,
yeah. Yes, sir.
right. So now let's look at the slightly alternate definition. So in order to get this alternate definition, we will do some calculation. Okay. So the first calculation that I'm going to do is assume that you know that n of t is Poisson. Okay. So let's assume that n of t is Poisson with rate lambda t. Okay. Now suppose n of, let's say, a small interval delta, right, equal to 0. What does that, what is the answer for this? Okay, so I'll write the picture. Picture looks like this. So if you have 0 delta and no arrival here, nobody arrives here, what is the probability of this? Assuming this, hey, you guys should tell me this. What is n of delta? Are you guys there?
Sir, we should just replace n equal to 0 in that distribution, Poisson's distribution with lambda
Exactly,
t.
right? So what is the answer? Huh? What is the answer? Okay, I'll write what is Poisson. You should remember
Yeah,
this.
sir.
Lambda t power k e power minus lambda t over k factorial. Okay. So what is it that you will substitute? First thing is you substitute delta in place of t, right? And then I'm asking the number of arrivals is 0. So what should I substitute here?
K should be 0.
K equal to 0. So what do you get? Right? Lambda delta whole power 0 is 1. 0 factorial is 1. The only thing that is left over is e power minus delta. What is this? This is e power minus lambda delta plus lambda delta square by 2 factorial minus and so on, right? This is what we get. Okay, do you agree?
Yes, sir. Yes, sir.
So now if you look at this, right, if you look at these terms here, these terms, right, when I divide by delta and take delta to 0, I get 0. Do you agree? Okay, so let's call this as g of delta. Okay, this whole expression. Note that limit delta tending to 0, g of delta divided by delta is 0. You agree?
Yes, sir.
Okay. So whenever you have a function g of delta such that g of delta or delta as delta goes to 0 is 0, we say that g of delta is small o of delta. Okay. So small order of delta essentially means that when you divide by delta and take delta to 0, you get 0. That means the order of, so the expression looks like some constant times delta power 1 plus something, delta power 1, 2 plus something, and so on. Okay. Is this clear?
Yes, sir.
Everyone? This is called the Landau's small o notation. Okay. Landau was a physicist. So therefore, this implies that the probability, oh my God, I hate Windows, that's why. Sometimes, see. Okay. Now it's everything is gone. Yeah, everything is gone. Okay. So I'll just quickly write this. Probability of n of delta equal to 0 is e power minus lambda delta. This is 1 minus lambda delta plus lambda square delta square by 2 factorial minus and so on, right? We call this as g of delta. So we saw that limit delta going to 0, g of delta by delta is 0. So this is nothing but g of delta is what is known as small order of delta. Okay. So this implies, I don't know, so some issue. This implies probability that if you look at n of delta, that is the number of arrivals in a small interval delta is 0 is 1 minus lambda delta plus small o of delta. Do you agree?
Yes, sir.
Everyone? Right? I can write the higher order terms as small o of delta. Okay. So if you assume that the process n of t has independent increment, right, then it doesn't matter where you ask this question, right? So for example, if you take this time axis, you take a small interval delta here or you take a small interval delta here, it doesn't matter. The probability that the number of arrivals in this case being 0 or here being 0 is the same. It's 1 minus lambda delta plus order of delta. Fine. So when your delta is very, very small, this order of delta will be almost 0, and the probability goes up to 1 as 1 minus lambda delta linearly. Okay, so lambda is very, very small. Sorry, delta is very, very small. Okay, is that fine?
Yes,
Is that fine? Okay. Now the second case is, what if I do probability of n of delta equal to 2? What do you think?
same thing, sir. We have to put k by 2 and find out the.
Yeah, so it's same, right? So
Yes.
I have lambda. Okay, let me write this: lambda t power k into e power minus lambda t over k factorial, right? K will be 2 here, so it will be 2 power 2, right? K is 2. Delta squared e power minus lambda delta divided by k equal to 2 factorial, right? So this 2 and this
So
2
that
cancel.
should be lambda.
Huh?
That should
Which
be
one?
lambda in the above equation. Lambda square.
Oh yeah, I'm sorry. Good. This will be 2. This will be lambda squared. Is that fine? Okay. So what is this? Lambda squared delta squared, right? And I have by 2, right? Do you agree? Oh, I'm sorry. Why did I jump to 0? I should jump to 1, right? So let's look at 1. Okay. Is this fine? So what will be the answer now? Okay. So what will be the answer? It will be lambda delta power 1. So it will be lambda delta. Okay. E power minus lambda delta by 1 factorial. So I can still write this as 1 minus lambda delta plus what? Lambda squared delta squared by 2 factorial minus and so on. Okay. So when I multiply, I get lambda delta minus lambda squared delta squared plus lambda cube delta cube by 2 factorial and so on. So this is nothing but lambda delta minus small o of delta. Do you agree? Is this fine? Okay. Yes or no?
Yes, sir.
Yes. Okay. Now, what can you say about probability of n of delta being greater than or equal to 2? This is 1 minus, right? Probability of n of delta is less than 2, which is equal to 1, right? That is what you will get. Do you agree? Is this fine? Okay, let's do this anyway. So let's do it from the first principle. What is this? Greater than or equal to 2?
Should do it for k equal to 2, 3, 4 till infinity.
Yeah. So or we can do it
Or
for
1 minus less than or equal to 2.
less than 2, right? Less than or equal to 2.
Less than.
Yeah. 1 minus probability of this less than 2. Let's see if this works. Less than 2, less than or equal to 1, right? This is 1 minus. What is probability of n of delta less than or equal to 2? It essentially means that n of delta is equal to 1 or n of delta is equal to 2, right?
0 or 1.
0, sir.
Sorry, 0 or 1, right?
1,
So
yes,
it takes
yes.
0 or it takes 1, right? They are disjoint events, so it will be sum of the two, right? Probability of n of delta equal to 0 plus probability of n of delta equal to 1. So what is probability of n of delta equal to 0? It's 1 minus lambda delta plus order of delta, right? Plus what is probability of n of delta equal to 1? It's this, right? Lambda delta minus order of or plus order of delta. I think I should write it as plus. Okay. So what do we get?
2 times order of
No, this cancels. 1 and 1 cancels.
Delta.
So you get order of
Delta.
delta. Right. That means if you ask the question whether there will be any arrival in a very small window of delta, the answer is 1 minus lambda times the size of the window, right? Plus some higher order terms which you don't get. If I ask what is the probability that n of delta equal to 1, then again it's lambda delta plus higher order terms, right? If I ask what is the probability that more than 2 or more than 2 or more than 1 arrives in a very small interval delta, the answer turns out to be a very small number, right? So it's order of small o of delta. Okay, is this fine? Okay, now I can define Poisson process as follows. Maybe I can just show one nice. I think I have one nice. I think this is the one. Yeah, this is a nice website. Okay, make a note of this. Okay. Okay, so this is how I can define Poisson process. So you take a rate lambda. So this is your rate. Okay, and you have a counting process n after t is said to be Poisson process with rate lambda. If n of 0 is 0, that means in a small window you cannot have any arrival. N of delta, n of t has independent and stationary increments. We know what that is. And also we have this property. Okay, take any window delta, this is satisfied, right? This is what we proved. Do you agree? Right?
Yes, sir. Yes, sir.
Yes, sir.
Right? This is an alternate definition for Poisson process. Okay, maybe I'll should I write this or do you want me to write this?
No, sir, it's fine.
Huh? I'll just write this. Let lambda greater than 0. We say that n of t is a Poisson process if A, n of 0 is 0. B, n of t has stationary and independent increment property. Independent increment, you know what that is, right? Property. Third, okay, probability of n of t, n of delta equal to 0 is 1 minus or 1 minus lambda delta plus order of delta, right? So B, probability of n of delta equal to 1 is lambda delta plus order of delta. C, probability of n of delta greater than or equal to 1, 2 is equal to what? Hey, is this correct? It's order of delta. Okay. Then we say that the arrival process n of t is a stationary Poisson process. Okay. Okay, I'll just make one small change here. So we say that n of delta. Okay, now I think I'll just stationary Poisson. Well, I'll call it a stationary homogeneous Poisson process. Okay, homogeneous Poisson process. If okay, is this fine? So suppose I want to remove this. Okay, homogeneous. Then what should I do? Let this lambda t equal to t greater than 0. Okay, this is something very has stationary and independent. Well, independent I'll just remove. Increment. Well, independent is fine. Yeah. Okay, independent. Okay, independent is fine. Okay, increment property. What do I do here? I'll just take these things. Okay, it can change over time. It's called non-homogeneous stationary, non-homogeneous Poisson point process, or not point process, Poisson process. Okay, is this fine?
Yes, sir.
Okay, now
Sir,
yes.
can you explain about order of delta then?
What is order of delta? What do you mean by this? This essentially means that if you look at these expressions, right, whatever that is there, for example, that is g of delta, okay, the exact expression. Okay, if you divide by delta, this goes to 0 as delta goes to 0. So if this happens, instead of writing g of delta, I'll say order of delta. Is that fine? G of delta can be, some constant times delta and some function of delta,
Hello,
right?
sir.
Yes.
Even g of delta alone will go to 0, right? As delta tends to 0.
Yes, sir.
That is true, but what I'm saying is even by dividing, what is the difference between g of delta going to 0 and g of delta by delta going to 0? What is the difference? What can you say about g of delta?
There is one more delta in the
Exactly, right? The first order term is also there, and
second order term.
yes, right? Yeah. So in fact, if g of delta or delta goes to 0 as delta goes to 0, that essentially means that
It goes
g of
mostly.
delta is of the order of, it has a delta squared or delta power 1 plus epsilon term. Okay. Is that fine?
Sir,
Yes.
in case of central limit theorem, sir, you have used bigger O of
So what is the difference between bigger O of delta? Okay, we say that g of delta, or I don't want to use delta. Okay, let me use something. Okay, g of x. Okay, is big O of x. What does that mean? What do you say? Okay, or let's look at something else. Okay, big O of f of x. What does this mean? This essentially means that if you take the ratio g of x over f of x and you take x going to infinity, this goes to a constant. Okay, then we say that the ratio, we say that g of x is order of f of x. Okay, so this also implies that f of x is equal to big O of g of x. Okay, see, if you are looking at asymptotics, then this makes our life a lot easier. You need not worry about all the constant, right? All the terms. Just say, look at order. Makes it very, very convenient. Okay? Is that fine or no?
Yes, sir.
Yes, sir.
Okay. For example, g of x is x squared. Okay. Now, I cannot say that g of x is small o of x squared. Right? Why? If I divide by x squared and take x to 0, I get 1. I won't get 0, right? It won't satisfy this. But I can say that g of x is big O of x squared, because in fact it is equal to x squared. Or I can say that this is big O of 3x squared, because if I take the ratio, it goes to 3, right? It's a constant. Okay?
Sir, can we say small o of x?
No, right?
Yeah.
What
X
is that?
squared by x.
Huh?
Small o of x.
Yes, you can
Can
say that. Yeah. Right, because if you divide by x and as x goes to 0, this goes to 0. Yes, well, it's slightly bigger than that, right? So you can write it. Yes. Okay. Formally write the definitions of big O of something and small o of something. Okay, this will be your homework. You should submit it as a part of next homework. Okay, is that fine? Okay.
Yes, sir.
Okay. Shall we move on with this definition? Okay. So now there is another way of looking at this Poisson. Okay. So, okay. Let's look at this picture. This is, I'll divide this into n slots, 1, 2, 3, 4, n, right? I'm going to toss a coin. If it is head, I'm going to first outcome is a head. I'm going to write head here or tail. Okay, head, head, and so on. Okay, I'll fill this. This is like NIID Bernoulli trials, right? Or tosses. Is this fine? Let's assume
Yes,
P
sir.
is the bias of the coin. Okay. If I ask you, what is the probability that we observe k heads in n tosses? So let's suppose xn is number of heads in n tosses. Do you agree? Okay. I can also look at it as an arrival process, right? Whenever there is a head, somebody arrives in the first lot. Again, I toss a coin. If it is tail, nobody arrives. If I toss again in the third slot, somebody arrives. Fourth slot, somebody arrives. So if you look at this interval, right? There are three individuals arrived in 4 slots. So I can also think of this Bernoulli process as an arrival process, right? So there are people arriving. Do you agree? Agreed or
Yes,
no?
sir. Yes, sir.
Yes.
But your arrival instance will be discrete.
Yeah, it's discrete, right? Do you agree? Okay. Now, what is the probability that xn equal to probability of k tosses in n heads? What is the answer?
Binomial.
What is binomial? N choose k, p for k, 1 minus p for n minus k. Do you agree? Do
Yes,
you
sir.
agree? Okay. Okay. So, okay. Now we will make some assumptions here. Okay. So now, if I say that this ratio k by n, right, goes to p. Okay. If k by n goes to p as n goes to infinity, right? Okay. Now, what can you say about limit n going to infinity? Well, oh, okay, sorry. It goes to p as n goes to infinity. Okay, what can you say about this? What can you say about this? What is it that you can say about this?
So to the limit of this nck p to the power k 1 minus p all to the power n minus k, and then we have to find that limit of this function only, sir.
Yeah. So what can you say
So
about?
so 1 factorial.
Probability will be very less, no, sir.
What is that?
The probability that this event occurs will be very less
So,
because
okay,
1
sorry,
minus p power
I
n.
think I didn't mean this. Okay, so if it is k over n, obviously goes to. Okay, so let's evaluate this and see what is it that we want. Okay, so let's look at this thing. Okay, so limit n tending to infinity. Okay, this will be n factorial n minus k factorial into k factorial. This will be p power k 1 minus p power 1 minus p power n minus k, right? Do you agree? Now, when do you think that this looks like a Poisson arrival? What should be the condition? Okay, so I think I'll just show this. This has a nice diagram. If it is there, then I'll show. Otherwise, I'll write it. It should be here. Yeah, somewhere here. Okay, so fine. Okay, so now, okay, let's look at this. This is P is the so okay. So let me just draw here itself. Okay, so now, okay, so let's keep this for a moment. Okay, so now I have head tiles, right? So we have this head tiles, head, tail, head, head, and so on. And then let's say tail. Okay, this is what we have, right? Let's consider this interval as small delta. Okay, these are all small deltas, and this is time t 0 to t. Okay, now what is this saying? So if I assume that the probability is p, right? Do you agree? Probability of head to occur is p. That means in an interval delta, there is one arrival with probability p, zero arrivals with probability 1 minus p. Do you agree? On an average, how many arrivals will be there? So if I say that lambda is the average number of arrivals, right, per second or per unit time. If lambda is this, okay, so what can you say about p? P is nothing but lambda times n. So essentially, when you toss n times, lambda and fraction of the times, you will have. You understand what I'm saying, right? Okay, so this lambda is essentially is of the order of p by n. Okay, is that fine? So that's what we. Sorry, I'm sorry. So in this case, okay. So if the lambda is the average number of arrivals per unit time, how many arrivals on an average will be there in in delta seconds? In lambda arrivals, okay, lambda arrivals in 1 unit time, right? In delta unit time, how much you will have? It's lambda delta arrival, right? So that means lambda delta is the average number of arrivals in time interval delta. So let's call this as P, okay? This is my probability of head to occur. Do you agree? This is how I can mimic my, at least on an average sense, my Poisson arrival. Do you agree? Yes or no? Yes?
Sir, can you please explain
Huh?
I didn't get some.
Okay, fine. I'll explain it again. So what I'm trying to do is there are, so let's assume that I have a time interval 0 to t. Okay. I'm going to divide this time interval into small intervals, delta. Okay. Is that fine? So
Yes,
let's
sir.
say n delta, okay, is t. So I'm going to divide the interval t into n intervals of size delta. That's what I'm saying. Do you agree? Okay.
Yes, sir.
Now in each interval, right, in this thing, there will be an arrival with probability p. There will be no arrival with probability 1 minus p. That means I'm going to toss a coin. If it is head, with bias p. If it is head, there is an arrival or no arrival. Okay. So how am I going to choose this arrival or the probability p? It's some lambda times delta. Delta is the width, lambda is very small. Lambda is the arrival, the average number of arrivals per unit time. So suppose I have a Poisson arrival with rate lambda. I'll take this lambda and multiply by delta. Delta really small, so that is equal to p. Do you agree?
Yes, sir.
Okay, fine. Now with this, I can sort of mimic what is known as the Poisson arrival. Okay, so the question is, how do you do that? Okay, so now how many arrivals will be there in t seconds in this case? Right? How many arrivals will be there in t seconds? There can be 0 arrival, there can be 1 arrival, there can be 2 arrivals, and so on. There can be k arrivals, right? So if there are k arrivals, how do you write that? Probability of n of t equal to k is what? It's there are the total time is what? N delta, right? There are n slots or n delta slots, or right? So n there are totally n slots, and I have k arrivals. That means n choose k, p power k, 1 minus p power n minus k. Right? This is the Bernoulli, the binomial. Do you agree? It comes from tossing of a coin. Is that fine?
Yes, sir.
Okay. So now I have divided this whole t into n interval, right? Or n is nothing but t by delta, right? That's what I have done. Okay. So now I can look at this whole process as binomial with n arrivals and p. Do you agree? Do you agree with this? I don't know how to highlight this in this particular thing. Is that fine or no? Yes. Okay.
Sir, can you please repeat, sir, this one, please?
Okay. P is lambda delta. That is something that you understood.
Yes, sir.
Okay. N delta is T. That is something that you understood.
Yes,
Okay.
sir.
So now I'll write this in this fashion: n factorial n minus k factorial into k factorial p power k 1 minus p power n minus k. Right? This is Bernoulli.
Yes,
So
sir.
what I'm going to do is I'm going to take this, substitute lambda delta for p. Okay, wherever I find p, I'll just substitute it as lambda delta. Okay.
Yes, sir.
Okay. Now wherever I find the other thing, right? N, right? I'll substitute it by t by delta. I can do that,
Yes, sir.
right? Well, I have to be careful here in the sense t by delta need not be integer. Do you agree? It can be a fraction.
Yes, sir.
So I have
Yeah.
to either seal or floor accordingly. Okay. If I substitute it here, I'll get an expression which is some function of lambda delta nt. Do you agree?
Yes, sir.
Okay. Now what I'm going to do is I'm going to take delta to 0. Okay. Delta I'll tend to 0 and see what happens to this expression. Okay. This expression turns out to be lambda t power k over k factorial e power minus lambda t. Okay. It goes to Poisson. That means what is it that I'm doing? I'm taking an interval. Okay, so let me write it again. Sorry, I'm going back and forth. So I'm taking an interval 0 to t. I'm making this, I'll divide this into small intervals, okay, of size delta, and I'm going to say that there will be an arrival with probability p and no arrival with probability 1 minus p. I'm going to toss a coin, okay. Now if I count the number of arrivals n of t in this interval, okay, as delta, the interval goes down to 0, this n of t will eventually go to Poisson with rate lambda. That's what it says. What is lambda? What is lambda? It is this, right? P over delta. Okay. That means I have to shrink my the p also. Okay. So that means as delta goes to 0, p should also go to something. It should also go to 0 such that the ratio goes to lambda. Okay. That's how I'm going to change everything. When that happens, the number of arrivals in t seconds will approach Poisson. Okay, this is an alternate way of describing Poisson. Okay, another interesting homework would be generate approximate. Okay, so I'll just say approximate Poisson with rate 2 lambda equal to 2 using binomial. Okay, using Bernoulli. Okay. Can somebody do this? Or in fact, this is homework. So everybody has to write a program to do that. Okay, where are you guys? No, it's not. Yeah, it's here. Is this clear? Okay. Mathematically, you can prove this. It's not that difficult. Okay. So we'll prove that in the next class. This proof, right? You can take it as a homework and see this proof that I talked about. I think you understood this argument, right? So use that and take the appropriate limits. You should get exponential. Okay. Fine. So where do you get? Okay, I can give you some hint. So e power minus lambda t. So how do you get this? 1 minus
lambda t over
power
n or something. N, sir.
This is the one, right? As delta goes to 0, this should go to. Hey, I'm sorry.
1 by delta.
Yeah, you're right. Right?
Yes.
Okay. Now, what is lambda by? Where is that? What is lambda delta? It's p, right? Lambda delta is p. I think it's just check this thing.
It should be 1 by delta in the power.
What is that?
1 by delta in the power, I think.
So I'll just do this. Okay. Lambda delta t power
1 by delta.
Hey, what is that, man? So 1 minus x power 1 by x, right? This goes to e power minus 1, right?
Yes.
A goes to e power a, right? So that means if I have lambda delta, this goes to, I should have 1 by delta. Okay. This thing goes to e power minus lambda. So you will get this y.
By the second term of the binomial, sir, like 1 minus. So by the second term of the binomial, you have written, no, sir?
Yeah. So you get 1 minus p whole power
n minus k. So we have to split that one.
Power n minus k, right?
Yeah. So we have to split that.
Yeah, so just check this. I might be off by some constant here, but this is how you get e power minus lambda t and the other things. Okay?
Okay, sir.
Trust me, it's not that difficult. If you don't get it, I'll do it in the next class. Okay, to summarize, we have two ways of generating Poisson. Start at 0, generate an exponential random variable, okay, x1, there'll be the first arrival, another x1 plus x2, there'll be another, and so on. Okay, this is one way. The other way is 0 to t, divide this into small intervals, okay, very small delta. You have 1 here if with probability p, 0 otherwise, and do this. Okay, you have to choose the probability p in such a way that if you look at p times the number, right, n, right, that should tell me the average number, right, the number of heads in this. So how many arrivals per second? Yes, Pn by t is your lambda, right? So that should be your arrival. That's how you choose your Pn, and so for a fixed t, you choose your delta. So t by n is what? Delta, right? So this will be p by n is your delta. Sorry, lambda, right? Lambda n is your p. That's how you choose. You choose your p as lambda n. Okay? You understood what is the process?
Sir, P by T will be delta, no, sir?
P by T, no. See, T by N is delta. Okay?
Yes, sir.
Okay.
1 by.
So now if you say lambda packets per second, okay? So 1 second you will have lambda packets. In T seconds, T lambda packets, right?
Lambda T, yes.
Right? Or the other way is 1 second you will have t seconds will be have t lambda, right, packets. Now t by n is delta, I have to relate it to what? P, right? So how do you say what is the number of packets arriving on an average in t seconds? Pn, right? N slots. But what is n?
Yes.
T by delta, right? So this is what? You understood, right? So you should, what is the average number of arrivals here? It's P into N, right? That's the average number of, the total
Delta
number,
into N.
right? In T seconds. In 1 second, Pn by delta should be lambda. Pn by T should be lambda.
Yes.
Or P should be lambda T by N. Okay? Okay, anyway, so
Yes, sir.
I'll detail this in the next class. So the next class we'll do two things. I'll just take the Bernoulli and or the binomial and show that properly that it goes to Poisson. And the second thing is merging and splitting of Poisson, and then we will move on to Gaussian. Okay, Gaussian random vectors and all that. Okay.
Okay.
Okay. Yeah. Okay. With this, I'll stop. We'll meet. Savan, can you